Good afternoon, everyone. I'm Han Ling from Group 7. The topic of our implementation project is a GAN-based friend generation framework to improve social recommendation. My group members are 钟瑞超、马潇、徐运志、刘金芳, and me. We will talk about our model in the following subtopics. First of all, let's have a glimpse of our algorithm, RSGAN. The algorithm has three parts: preprocessing, generator, and discriminator. In preprocessing part, we first obtain user data as well as item data to build an heterogeneous information network, HIN, which will be discussed in the next slides. Then we generate user embeddings for each user in HIN in order to get the seeded friends. In generator, we use collaborative denoising autoencoder, CDAE, to enrich the user's seeded friend by finding his or her latent friends. Afterwards, one friend will be sampled through the Gumbo softmax technique from these friends as the user's reliable friend. And one loved item of the reliable friend will be sampled out to recommend to the user. While this is the generator part. While in a discriminator, we take in the sampled item as the generated item. Then the recommended item will be ranked by BPR as a feedback to the generator. As for output, the discriminator will produce the top unliked item of the user.
Hello everyone. I'm Rachel Jones. Today I'm going to talk about the data preprocessing part of our project. Here's the overall graph about the data preprocessing parts in our project. First, I will talk about how to construct a heterogeneous information network. And the input data sets in this project can be represented into two kinds of bipartite graphs, which are user-user graphs and user-item graphs. Although there are different kinds of graphs, they are inherently correlated due to the fact that the user nodes here are in the both bipartite graphs. In order to enhance the shared information between two bipartite graphs, we use the user node as a connected node to construct the HINs and build a metapave table, which will be illustrated in the next slide. And this graph shows how we construct the heterogeneous information networks from these two bipartite graphs. And then after that, we are going to talk about the embedding representations learning. After generating the HINs, we need to do some embedding representation learning, which is actually the metapave to vect. It can be divided two parts to illustrate, which is metapave-based random walks and the heterogeneous skip grants. The metapave-based random walk is that perform a random walk in HINs based on the pre-specified metapave tables, which is shown here. In order to construct a node sequence and capture the semantics and structure meaning of the information network. Then, after obtaining the node sequence from the metapave-based random walks, we need to do the heterogeneous skip grants. Extending skip grant to information network analysis, the idea is pretty simple because the skip grants is used to word to vect usually. which is the idea is pretty simple, which is to use the concept of word contest by doing random walks on the information networks. Think of each random walk path as a sentence. The focus nodes can be regarded as a focus word in the word to act, and the neighboring nodes of the focus node can be regarded as the context related word vectors, and then use the same skip grant model to complete the network embeddings. And after that, we can get the user information's embeddings. And note that we have two social corpora which depicts the positive and negative user preference respectively. So after getting the network embedding of the users, we compute the cosine similarities for each pair of user with respect to their embeddings and identify the top case positive and negative implicit friends for each user. We divide friends into three parts, which is shown here. In detail, we define the implicit friends who share similar positive preference with the current user are called positive friends. The negative friends are the implicit friends who share similar negative preference with the current user. The perfect friend is the implicit friends who share both similar positive and negative preference with the current user. After that, we can get a set of perfect friends and label them as the C friends and fit them into the next part, which will be illustrated by my partner next. Thank you.
Hello everyone, my name is Liu Xingfeng, and in my part I will give you some brief idea of social profile reconstruction. Since the number of seeded friends generated from the heterogeneous information network is not large enough to improve the recommender system, and there may exist other latent friends in the user's social network, we have to apply the CDAE to reconstruct the social profile to find all latent friends of the user to improve the quality of the recommender system. Since we use collaborative denoising autoencoder, the function of the denoising autoencoder is to remove the noisy of the input part and generate the complete one, the no noise one. And the noisy in our task is the people who are not tagged with friends or not friends, which means we don't know whether these people is the user's friends or not. So we feed the seeded friends with the noisy into the CDAE. Then the CDAE will generate the complete social profile of this user to find all latent friends. And in this part, I will give you some intuitions about the CDAE. The input part I have mentioned in the last slides. We feed the seeded friends with the noisy. We want to remove the noisy. And there is another extra nodes in the input layer. It is different to different users. It represents the user's preference to make friends. It makes sense because different user may have different preference to make friends. For example, like me, I would like to make friends with somebody who like to travel, and maybe you like to make friends with somebody who like study. So it makes sense to have this node here, and different people have different user node. The CDAE then will encode the input part to the latent representation of the user's preference. And then the CDAE will decode the latent representation of the user's preference to reconstruct the user's social profile and find all the latent friends of the user. Our task in the eye scan is to find the most reliable friends. To pick the most reliable friends, we need firstly apply the softmax onto the output layer here to calculate the probability of different friends of the user. And then the simplest way is just to pick the highest probability as the reliable friends. But there is a problem. In this way, pick the highest probability, we cannot apply the back propagation on our model while we're training the model. So we need to figure out another sample technology to pick up the most reliable friends from this output layer. And next, my partner will introduce you the sample method.
Okay, hello, I am Xiao. So now let's come to the sampling part. You can also think it as the major work of generator of RScan. Here we will first do friend sampling and then item sampling. By the way, you may ask why not generate items directly? The brief answer to this question is that there are too many possible items. We want to simplify the process by reducing the number of items involved for recommendation. So we use the supervision of their friends. More specifically, their latent reliable friends. Well, now, in order to meet the requirements of the end-to-end solution, in other words, to make the whole process derivative, a trick called Gumbo softmax is used here, and it is an approximate calculation of random sampling. This is the formula we used here. Okay, so this is a continuous and differentiable calculation where V is the generated vector that is basically one hot vector. There is also the hyperparameter tau, which is called temperature. The smaller tau is, the closer the sampling results are to one hot vector. And there is also the noise vector, whose elements are randomly drawn from Gumbo 0 to 1. So in this trick, we decoupled the sampling procedure from the training process and enabled gradients flowing without changing the behavior of the model. Meanwhile, the noise brings some randomness to the sampling procedure, which helps to avoid the overfitting problem and enhance the model reliability. So the input of friend sampling is the possibility distribution of friends, and the output of it is V, which is one reliable friend each time. Okay, after we sampled reliable friends, likewise, we will use Gumbo softmax again to sample the item consumed by this friend. However, the possibility distribution of items is generated differently. Here, we use matrix H to represent the score of every item for each user, whose elements are averagely initialized, and they are going to be updated during training. The steps of item sampling can be defined like this. So the output of item sampling is a reliable friend, and the output of it is a one hot vector representing the sampled item. And after it is sampled, it will be sent to the discriminator, which brings us to the next part of this model. So now let's pass time to the next speaker. Thank you.
Hi everyone, I'm Xuying. Now let's move on with my part of the presentation. In this project, the discriminator of GAN is constructed with the BPR model, short for Bayesian Personalized Ranking. The primary task of personalized ranking is to provide each user with a ranked list of items. More specifically, a user item ranking score matrix X. As a pairwise approach, BPR transforms implicit feedback data into triplet Uij, which means user U prefers item I over item J. And then BPR uses matrix factorization to simplify the optimization of target matrix X. What a matrix factorization does is that it decomposes a large matrix into products of matrices. Like here, matrix X is broken into matrices W and H. Most importantly, the Bayesian formulation of finding the correct personalized ranking for all items is to maximize the following posterior probability, where phi represents the parameter vector of an arbitrary model class, for example, matrix factorization. So in the project, from the former step, we have received the generated item Z, and then we need to get one positive item sampled from what the current user U has consumed, and one negative item sampled from what the current user U has not consumed. In order to impose a social constraint to the BPR model, we make an assumption that users tend to assign higher ranks to the items that their friends prefer. In other words, in the target item ranking score matrix produced by BPR, the ranking score of positive item should be bigger than that of generated item, and the ranking score of generated item should be bigger than that of negative item. So with the mechanism of BPR, we can finally get the top K items for each user. Okay, my part is done, and my partner is going to show the results of our experiment.
Here, I'm handing again. We run the code with the settings mentioned in the original paper, and we get the results as follows. We compare the RSGAN model with BPR, SBPR, TBPR, NuMF, IFBPR, and CFGAN. Note that the IFBPR is also proposed by the same author of RSGAN. In the results, we found that the IFBPR obtains the best performance, while the RSGAN is the second best. We suggest that only 100 iterations of training might not be enough for RSGAN to gain its best performance. We also compared our new RSGAN with the original RSGAN in the paper, and we are very glad to tell that the new RSGAN performs better than the original RSGAN in all dimensions. This is our experimental results. That's all. Thank you very much for your listening.